Hi everyone. In this video, I'm going to talk about how to graph your surface area to volume ratio assignment. So I've already done the calculations for the sphere. The sphere had at radius 1 had a surface area to volume ratio of 3. The sphere at size 2 radius had a surface area to volume ratio of 1.5. So you'll notice that right from the start, we go from 3 increasing the size to 1 by 1, cut our surface area to volume ratio in half. And remember that we already talked about how efficiency is related to that surface area to volume ratio. So we learned the higher that surface area to volume ratio is, the more efficient it's going to be. And you'll notice that as the size of the cell increases, that surface area to volume ratio is decreasing, meaning that as the size increases, the efficiency is going to decrease as well. So you could say the opposite is true. The smaller the cell, so as we go smaller this way, that surface area to volume ratio is increasing. Therefore, the efficiency is increasing. And so this is a very important relationship I need for everyone to understand. Let's take this data now and see how we would graph it. So when I do this graph, I'm going to turn my paper landscape. So that means sideways. And along the y-axis, I'm going to put the surface area to volume ratio. And along the x-axis, I'm going to put the size of the cell. So I'm going to start with the data for the sphere. Now, when I look at my graph, I can see that at 1 meter, the surface area to volume ratio of the sphere was 3. So I'm going to go ahead and put a dot right here for the sphere. Next, at a size radius of 2, the surface area to volume ratio was 1.5. At cell size radius 3, the surface area to volume ratio was 1. At cell size 4, the surface area to volume ratio was 0.75. At a ratio of 5, it was 0.6. At a cell size of 6, it was 0.5. At a cell size of 7, it was 0.428. At a cell size of 8, it was 0.375. At 9, it was 0.33. And at 10, it was 0.3. And so when you look at the line that we would make from this graph, it would look something like this. And again, this is the data for the sphere. So now I'm going to do the same thing for a cube. And I'm going to use my data from the previous page. So those are my dots, and I'm going to do the same thing. I'm going to collect the lines. And that's the graph for the cube shape. Now let's do the rectangular solid, or the column. Again, I'm going to pull this data from the previous page. And so you can see from this line, the column doesn't have this dramatic drop in that surface area to volume ratio that you see with the cube. The cube goes from 6, and then it gets cut in half. That surface area to volume ratio gets cut in half at 2. And then it just continues to go down from there. For the sphere, the surface area to volume ratio is 3, and then as you go up in size by 1 micrometer, then the surface area to volume ratio again gets cut in half from 3 to 1.5. You don't see that in the column. The column maintains a very relatively high surface area to volume ratio. And so if a cell is going to have to be larger, it can change. If it's in this column shape, it maintains a very high surface to volume ratio, even if the cell's getting larger, like it does here on the x-axis. And if you think about why this is happening, let's take a look at the sphere as a classic example. So the formula for the calculations that we used are given to us, but I just kind of want to look at them a little bit closer. So when you look at the formula, this is our surface area over volume. I want you to notice that here for the radius on the numerator, the radius is squared. And for the denominator, the radius is cubed. And so if we use a random number, let's say the number 2, or we're going from 1 to 2. This will make a little bit more sense if we focus just on what's going on with the radius. So if the radius is 1, we have 1 squared, which is 1 over 1 cubed, which is still 1, no problem. But watch what happens when I change the radius to 2. 2 squared is equal to 4, but on the bottom, the denominator, 2 cubed, is not equal to 4. It's equal to 8. So the denominator is increasing faster than the numerator is because of this exponent. So what that means is, as the cells get larger, the volume, which is this part of the equation, is the bottom part is the volume. The volume is going to increase faster than the surface area does. So as your denominator gets bigger, your overall value becomes smaller. And so we've got to look at ways to keep the surface area very high without changing the volume. And so the way to do that simply by size is to keep the cells very small. Another way we can keep the cells efficient is figuring out a way to change the surface area without changing the volume. This can be done by infolding the plasma membrane. And then the last way we can try to keep a cell as efficient as possible is by changing the shape of the cell. And as we saw in the graph, the most efficient cell is going to be the column shape because it has the highest surface area to volume ratio. I hope this video was helpful. Thanks for watching. Bye-bye.